All right. So here we go. So this is a pretty simple problem to get started. You guys have probably worked harder ones than this for homework, but here we go. So you can see I've got a beam. There's on this little cantilever section, there's a distributed load of 2 kilonewtons per meter, and there's a point load roughly in the middle. This connection looks like a pin, so we're going to treat it like a pin, and this looks like a roller, so we're going to treat it like a roller. Okay? If you had this problem in the book, the author would tell you assume A is a pin and B is a roller, so there shouldn't be any question. So again, the first thing I'm going to do is I'm going to draw my free body diagram. It's pretty important, as I mentioned before. So I'm going to first copy the geometry. I'm going to assume, since B is a pin, I'm going to assume that BY acts up. Now this is what I do. You don't have to do it this way, but I don't like to think. You guys like to think? I try to avoid it whenever possible. So I just work on muscle memory. And my muscle memory tells me that up is positive, so I just go up. I don't even think about it. So I've got my Y force up at B, and I'll just go up at A. And then in the X direction, I always think left to right is positive, moving in the right, so I'll just do it like that. So I just make some assumptions for those 3 reactions. I'm going to transfer down the fact that I have this point load of 24 kilonewtons right in the middle, so that's 6 meters and 6 meters. I know it seems a little redundant to bring down the geometry, the dimensions, but I find that that will help you keep track of things, especially later when some of the geometry might get a little more complicated. Then I'm going to take this distributed load and I'm going to convert it to an equivalent concentrated load. So all you have to do is find the equivalent area under the curve. Rectangles are easy. It's just base times height. So the base is 3 meters. The height is 2 kilonewtons per meter, so that's 6 kilonewtons. I usually show that that's an equivalent by doing a double line arrow. So I'll put down my 6 kilonewtons. And now I know that that acts through the centroid of this area. And again, I know centroids for a rectangle, that's pretty easy, just halfway. So half of 3, it'll be hard to see here, but I'll just do it on one side. I'll say 1.5 meters. So I'll just review it real quickly. I've got my reactions at A and B. I like that. I brought down my applied loads, and I brought down my concentrated equivalent. I think that's all I need. So there's my free body diagram. So I'm almost passing the class by just doing that. Now, my other strategy I suggested to you was to, if possible, try to some moments about some point first. And in problems like this, I think it's a really easy application. If you look over here at A, which happens to be a pin, you can see that there are 2 forces that are concurrent there. So that's a great place to sum moments. So I'll do that first. So I will assume that right-hand rule, counterclockwise, is going to be positive moment. I do that all the time. I never not do that. Now, you don't have to do that. If it works better for you to go the other way, do it. But right-hand rule, you'll find later, is pretty typical. So then I will sum the moments about point A, and I'll make sure it's in equilibrium. That's not a trivial statement, right? And I'll underline that. That tells me a lot. It tells me where you're summing moments. It tells me your sign convention. It shows me that you're going to apply equilibrium. So let's do that. So let's sum moments about A. The 24 kilonewton force about A, with my sign convention, does it create positive or negative moment? Negative. So I'm just going to write the negative sign to start up. And of course, moment is force times distance. The force is 24 kilonewtons. The distance is 6 meters. So I'm just going to write down 24 kilonewton force times 6 meters. There's the moment effect of that. And what about my concentrated equivalent? Well, it's also a point load. So it will be positive or negative moment?
Negative.
Another negative moment. So that's 6 kilonewtons. And what's the distance from A to that centroid?
13.
Yeah, it looks like 12 plus my... I didn't note it there, but it's 1.5. So that's 13.5 meters. And then what else is creating moment about A? By. Positive or negative moment?
Positive.
Positive. So again, force By times distance, which is from A to B, 12 meters. Oops, not 13, 12. So you can see I have one equation in just one unknown, so I should be able to solve for By. I can't do it in my head, so I'm going to let you tell me what it is. 18.75. Anybody else get 18.75? Is it positive or negative? It's positive. 18.75. Don't forget your units, kilonewtons. And I'll do that. And this is where I like to stop and think. Okay, I got a positive value, so that means I assume the right direction. Does that make sense? Seems to make sense. I know this is a simple problem, but don't let those kind of basic insights, don't let those escape without being used. As the problems get more complicated and the directions start changing around, it's always good to kind of think about it and see if it makes sense. Now at this point I can go any way I want. I'm just going to go ahead and sum forces in the y direction, no particular reason why. So I'm going to assume up for positive, and I'm going to sum forces in the y direction and make sure it's in equilibrium. So just like my statement before about the moment, this tells you a lot. I'm summing in the y direction. I'm going to assume up is positive, and they have to be equal. So let's just go through and see what we've got. Well, I've got AY, it's up, so that's positive. I've got BY, that's up, so that's positive. I've got 24, that's acting down, that's negative. And then I've got the concentrated equivalent of 6 also acting down. And I would encourage you, too, to go ahead and just write the equation out the way it is. Don't say, oh, I already know BY, I'll go ahead and stick the number in there. I think that can lead to some issues down the road, too. Just go ahead and write it out. And since you know BY, it's pretty easy just to plug it right in. If BY had come out negative, let's just say, then you would just plug in a negative value right there. You wouldn't try to change the sign here, but your free body diagram says BY is acting up, and we've assumed up is positive. So don't mess with that. But if you get a negative value, just plug it in as a negative sign, a negative value. So that should be what, 11.25? And it's positive again. 11.25, and that's kilonewtons. So we're almost done. The last one's pretty trivial. You could have done this one at any time, but our final equation in our coplanar system is just to sum forces in the x direction and make sure we're in equilibrium. And I'll assume to the right is positive. In this case, all we have is AX. So I don't have to do much work there. That's an easy equation to solve. AX is 0. You might find that's true for a lot of our introductory problems, but as we move forward into frames, into truss structures, that's not always the case. That's it. We're done. Yes?
And just assuming we're doing this like as a homework problem or anything like that, does it say if we go from around 3 significant digits?
Okay, that's a good point. With mastery engineering, I think it tells you how many significant digits. Yeah, 3 is typical of structures. But you have to really pay attention to what they say. And also, I've heard over the years that they will tell you what direction is positive. So you might want to keep track on that. I don't know if you get to say up or down, left or right, clockwise, counterclockwise, or it may just assume, it may tell you. So don't lose points just because of a minus sign. So just, I know it's weird to say, but read the problem. It might help out. So any other questions about this one? You'll be lucky to get one like this on the exam. Really lucky, like lottery lucky. So.